Section: Introduction. In this section, we discuss diffusion models, which are used for generating high-quality images, videos, and other types of data. These models work by transforming complex data into a simpler Gaussian distribution through a sequence of distributions. By learning the score function for each of these distributions, we can create data from random noise through a process called sampling. However, this process can be computationally expensive as it often requires many evaluations of the score function. To make sampling more efficient, two main approaches have been developed: trajectory distillation methods and distribution matching approaches. Trajectory distillation methods aim to speed up the process of solving the differential equation involved in sampling, while distribution matching approaches focus on learning implicit generators to match the distributions learned by the diffusion model. In our paper, we introduce a diffusion distillation method called MCT. This method minimizes the difference between a pre-trained diffusion teacher model and a student model to enable efficient one-step generation from noise to data. We use a technique similar to the M framework to train the student model by alternating between estimating learning gradients and updating the model through gradient ascent. To improve the efficiency of sampling, we propose an alternative MCMC sampling scheme that updates both data and latent variables simultaneously. This approach simplifies hyperparameter tuning and enhances performance for short-run MCMC. Additionally, we identify a linear noise term in the learning gradient that, when removed, reduces variances in the optimization process. Through empirical studies, we demonstrate that our method outperforms existing approaches in tasks such as conditional image generation and text-to-image generation. Our results show that MCT achieves competitive performance with FID scores of 2.20 and 6.0 on ImageNet 64 and ImageNet 128 datasets, respectively. Furthermore, MCT shows promising results in one-step text-to-image generation by distilling from stable diffusion models. Section Summary. In this section, we introduce diffusion models that facilitate high-quality image and video generation by transforming complex data distributions into Gaussian distributions through a forward process. Sampling from diffusion models involves solving a differential equation, which traditionally requires multiple evaluations of the score function, leading to high computational costs. To address this, we propose MCT, a diffusion distillation method that minimizes mode-covering divergence between a pre-trained diffusion teacher model and a latent variable student model, enabling efficient one-step generation with competitive results in various generation tasks. Section: Maximum likelihood and expectation maximization. In this section, we will explain the concepts of maximum likelihood and expectation maximization, M. Expectation maximization, M, is a method used to estimate parameters in models with hidden variables. It aims to maximize the likelihood of the observed data by iteratively updating the parameters. The main idea is to find the best parameters that make the model's predictions match the actual data. The M algorithm involves two main steps, the E step and the M step. In the E step, we calculate the expected values of the hidden variables given the observed data. This step helps us estimate the gradients of the model parameters. The M step then updates the parameters based on these estimated gradients. One common application of M is in training generator networks. These networks can be trained using M by iteratively improving their ability to generate realistic data samples. By leveraging M, we can enhance the training process and improve the performance of the generator networks. Additionally, our method is related to other techniques like score distillation sampling, SDS, variational score distillation, VSD, and diff-instruct. These methods focus on distilling complex models into simpler ones for more efficient training and inference. In summary, M is a powerful tool for parameter estimation in models with hidden variables, and it can be applied to various machine learning tasks to enhance model training and performance. Section Summary. In this section, we delve into the expectation maximization, M, framework, which is a method for maximum likelihood estimation in latent variable models. Involves an iterative process of estimating model parameters by alternately computing the expectation of the latent variables and maximizing the likelihood function. This framework is crucial for training models where the marginal distribution is analytically intractable, and it can be applied to distilling diffusion models into generator networks by optimizing parameters through gradient updates. Section: Reparametrized sampling and noise cancellation. In this section, we start by considering Langevin dynamics for reparametrized sampling and noise cancellation. We use score functions to approximate the score of the student, which we do not have access to directly. Instead, we approximate it with a learned score network estimated using denoising score matching. This score network is estimated at various noise levels, allowing us to simulate Langevin dynamics at any noise level. Running Langevin MCMC can be costly and requires careful tuning, especially in scenarios like diffusion model distillation where different noise levels require different optimal step sizes. To address this, we reparametrize the variables x and z to simplify the joint MCMC sampling and step size tuning. This reparametrization involves a deterministic transformation from the pair of epsilon, z, to the pair of x, z, enabling us to push back the joint distribution to the epsilon, z, space. This reparametrized approach ensures consistent step sizes across noise levels, leading to improved empirical performance. However, training the student with these samples still pose challenges. Visualizing the samples produced by MCMC revealed significant noise, hindering the learning process. We discovered that noise accumulates linearly in each step of Langevin dynamics, impacting the quality of samples. By canceling out this accumulated noise and the initial noise, we obtained cleaner samples, crucial for successful training. Furthermore, we extend the approach to optimize a weighted loss over all noise levels of the diffusion model, ensuring alignment between the marginals of the student network and the diffusion process at all noise levels. This optimization involves coordinating multiple noise levels using a noise schedule and a shared generator across all levels. The final gradients for the generator and score networks are computed based on the MCMC sampling with noise cancellation. To update the generator and score networks alternately, we follow a similar approach to VSD. The algorithm for this process is summarized in the provided algorithm. Section Summary. In this section, we reparametrize sampling and cancel noise in Langevin dynamics for efficient MCMC sampling. By using a learned score network and a reparametrization of variables, we simplify step size tuning and improve sampling performance. Additionally, we optimize a weighted loss over multiple noise levels to match the marginals of the student network with the diffusion process, enhancing the training process. Section: Connection with VSD and Diff Instruct. In this section, we uncover an interesting connection between our method and variational score distillation, VSD. Even though VSD and our method are motivated by optimizing different types of divergences, we find that VSD is equivalent to our method with a special sampling scheme. By considering a specific scenario of our method with a step size of 1 in x, no update in z, and noise cancellation, we observe that the resulting gradient is exactly the same as the gradient for VSD, with only a sign difference. This connection shows that our method can smoothly transition between mode-seeking and mode-covering divergences by using different sampling schemes, ranging from biased sampling in only x to mixing sampling in both x and z. If we assume that the marginal distribution of x follows a Gaussian distribution, then our method's update closely resembles score distillation sampling, SDS. Moving on to related work, we discuss the challenges faced by diffusion models in terms of slow inference and the efforts made to accelerate the sampling process. Various approaches have been explored, such as developing numerical solvers for the phosphorus monofluoride ode and using knowledge distillation to condense the sampling trajectory of PF ode into fewer steps. However, these approaches struggle to significantly reduce the number of sampling steps without sacrificing perceptual quality. Recently, there has been a focus on one-step diffusion sampling models, aiming to achieve efficient single-step generation. These methods involve fine-tuning pre-trained diffusion models into single-step generators through adversarial training and trajectory distillation techniques. By adopting score distillation techniques, the distribution of the one-step generator's output can be aligned with that of the teacher diffusion model, enabling high-quality single-step generation. Despite their success in one-step generation, these methods often prioritize mode-seeking divergences, which may lead to issues like mode collapse. In our experiments, we apply our method to train one-step image generators on ImageNet datasets and for text-to-image generation. We initialize the student generators with weights from the teacher model and evaluate the results based on various metrics such as Frechet inception distance, FID, inception score, IS, recall, and clip score. Throughout our experiments, we refer to our method with k-steps of Langevin updates on both X and Z as MCTK, and specifically MCT1 corresponds to the formulation equivalent to diff instruct, VSD, with only one update in X as discussed earlier. Starting with ImageNet experiments, we demonstrate the impact of key components of our method including noise cancellation, multi-step joint sampling, and reparametrized sampling. We present results for ImageNet 64x64 and ImageNet 128x128 datasets. During our development, we emphasize the importance of noise cancellation after the Langevin update to improve training stability and convergence speed. We also investigate the effectiveness of multi-step joint sampling on both epsilon and Z, showing improvements in visual quality and structure. Additionally, we analyze the performance of the distilled generator concerning the number of Langevin steps per distillation iteration, highlighting improvements in mode coverage and overall performance with an increased number of Langevin steps. Section Summary. In this section, we establish a connection between MCT and variational score distillation, VSD, showing that VSD is equivalent to MCT with a specific sampling approach. By adjusting the sampling schemes in MCT, we can smoothly transition between mode-seeking and mode-covering divergences. Additionally, experiments using MCT for one-step image generation on ImageNet datasets demonstrate promising results in terms of various evaluation metrics like FID, IS, recall, and clip score. Section: Reparametrized sampling. In this section, we explore reparametrized sampling. We observe that the noise cancellation technique is independent of the reparametrization method. We can begin the derivation process from either the score functions of X, Z, or bold symbol epsilon, Z, to achieve similar outcomes. We compare two parametrizations for joint sampling, X, Z, corrector, and bold symbol epsilon, Z, corrector. For the X, Z, corrector, we adjust the step size of X to match the update magnitude of the bold symbol epsilon, Z, corrector. We maintain the step size of Z. This adjustment enhances numerical stability in the X, Z, corrector by balancing the terms in the score function. When comparing with existing methods, our approach, MCT16, which employs a bold symbol epsilon, Z, corrector with 16 Langevin updates, outperforms other approaches. We train on ImageNet datasets of different sizes and provide samples for evaluation. Our models excel in one-step distillation of diffusion models, achieving competitive scores on various tasks. We also test our method on text-to-image models by distilling the stable diffusion version 1.5 model using text prompts. Our approach, MCT8, demonstrates promising results in text-to-image generation tasks, surpassing existing methods in terms of FID scores and clip score. By tuning hyperparameters effectively, we achieve significant improvements in model performance. Additional qualitative results and comparisons with baseline methods can be found in the appendix. Section Summary. In this section, we explore reparametrized sampling techniques that are independent of the specific reparametrization used. By comparing joint sampling approaches like X, Z, corrector, and bold symbol epsilon, Z, corrector, we find that adjusting step sizes can impact the performance of the sampling methods. Our study reveals that while bold symbol epsilon, Z, corrector shows improvement over bold symbol epsilon corrector. The XZ corrector struggles to match the baseline, possibly due to differences in the MCMC friendliness of the parameter spaces. Section: Discussion and Limitation. In this section, we introduce MCT, a method based on maximum likelihood that uses an EM framework with new sampling and optimization techniques to train a student model matching the marginals of a pre-trained diffusion model. Our MCT method shows strong performance in generating images on ImageNet and in text-to-image tasks. Despite its promising results, MCT has some limitations that need to be addressed in future research. We observed that MCT performs best when the student model is initialized from the teacher model and is sensitive to the choice of T***, a fixed time step used during initialization. While our framework theoretically supports training the student model from scratch, we were unable to achieve competitive results in practice. A key future direction is to develop methods that allow generation from randomly initialized generator networks with different architectures and lower dimensional latent variables. Although MCT is efficient during inference, it adds computational cost during training due to multiple sampling steps per iteration and the need for careful tuning of the MCMC sampling step size. Balancing training cost and model performance is a crucial trade-off that needs further analysis and improvement. Exploring and enhancing the Pareto frontier of this trade-off presents an interesting avenue for future research. We would like to express our gratitude to Jonathan Heek and Lucas Thace for their valuable discussions and feedback. Sirui also acknowledges Dao Zhu, Jiawei Yu, and Zhishui Zhang for their support during a previous internship at Google DeepMind.